Okay, so I think now you know about the operation of serial in, serial out, shift register, right? So ultimately, whatever data that comes in here, okay, will be passed in one after the other, okay, and we'll be getting the serial data out. Fine. So the output of shift register occurs at rightmost flip-flop on the serial data out line. If the initial content of the four flip-flops is 1011 and a logic 0 is applied at the serial data in line prior to the positive edge of the clock signal, then students, you're not able to see the screen. So the output from shift register occurs at the rightmost flip-flop, and that is what we are very much aware of. If the initial content of the flip-flop is 1011 and logic 0 is applied at the serial data in line prior to the positive edge of the clock signal, then the content of the register becomes 0, 1, 0, 1. Okay. So it goes in the reverse order, right? So first this 1 will come, okay, and then 0. Yeah. So that is because this 1 is lost. Okay, this 1 is lost. Okay? And since initial 0, so that 0 will come and sit in here, right? Okay, yeah. So I think you understood how we are getting it. See, the initial data is going to be, let me write it here, 1, 0, 1, 1. So let us assume that this was our data initially. Okay, so as soon as there is a clock that comes in, the positive edge of the clock, what is going to happen is uh, this will actually get out. So which means this is lost. And if I initially give 0, okay, if I initially give 0, so that 0 will come and sit here. Okay, so which means this was initially at my first flip-flop, second flip-flop, okay, third flip-flop, and fourth flip-flop. So as soon as there is a clock, what happens is the content in fourth flip-flop is lost, and this content moves to the fourth flip-flop, okay, and this second one moves to the third flip-flop, and the content of first moves to the second flip-flop, okay. So this initial data that we give here moves to the first flip-flop. So our final value is actually going to be 0, 1, 0, 1. Any doubt here, students? Any doubt here? So this last value is pushed out. This last value is pushed out, and this 0 was the initial one. It comes and sits here. So this is our final value. Any doubts here? Is it clear? Can I proceed?
Sir, so that thing is only called a circular shifting.
No, it is not actually circular shifting. Circular shift will have a feedback actually. Okay, so if in case it was a circular shift, then this should have come and sat here, right? But that is not happening. This bit is getting lost completely. It's getting lost. This bit is completely getting lost, right? So it's not a circular shift. It is just shifted, and it's unidirectional. Remember, it is unidirectional. It is not bidirectional. Okay. Understood? Any doubt here? Any doubt here? Okay, thank you for that confirmation. Right. So sometimes what will happen, I do not want to lose this data. Okay, so whatever data was here, I do not want to lose. So instead, what I can do is I can connect a small feedback and I can give to the input side. So that is in fact called your circular shift registers. Okay. Now what we were looking here is the shift register. Okay. Only shift register. But if we have a small feedback connected, then that becomes a circular shift register. So keep this in mind. These concepts are important. Okay. So when I say circular shift register, can you tell me what is the output going to be? If my initial data was, let me put it up here, initial data was 1, 0, 1, 1. After one clock given, what is going to be my output? After one clock signal, what is going to be my output? If you have understood, you should be able to answer this. If it's a circular shift.
So will it be 0101?
No. If it's a circular shift,
With
think,
circular shift, it will become 1101.
exactly. So this one will come and sit here, right? So ultimately, what is going to happen? I am going to get value 1, 1, 0, 1. So this bit is gone there. This bit will come and sit here. So which means it becomes 1, 1, 0, 1. So if it's a circular shift, if it's not a circular shift, then this last bit is lost. Whatever we give initially, that will come and sit here towards the LHS, towards the left hand side. Right? So this is the concept. Circular shift registers are used wherein the serial data out is connected to the serial data in. So this is the feedback that I'm talking about. Okay? So this is the feedback that I'm talking about, where your serial data out is connected to the serial data in. So which means part of the output is connected to the input. So in that case, what is going to happen? In that case, we are going to get a uh, output, okay, wherein this bit is not lost and it comes and sits in the front. Okay. So if the content is 1011, okay, then after our shift, okay, it is going to become 1101. Yeah, of course, this is going to come and sit here. So I hope these are clear with you all. Right? Fine. So this is our example. Okay, we can actually create few examples. We can create problems, and I can give you some data here and tell you how or what is going to come up at the output. Show the states of 5-bit uh, shift register for the specified data input and clock waveforms. The registered is initially cleared. Okay, in fact, it should be the register is initially cleared. It's not the register. Okay, the register is initially cleared. Okay, so which means there is no data initially. Okay, and these are 1, 2, 3, 4, 5. How many number of flip-flops are there? So many number of bits you're going to get. So that is your first clue. Okay, so once you have that, okay, you can think of analyzing your data. So I have my clock signal. So these dotted lines are showing that it is happening at positive cycle or the negative cycle, positive edge or the negative edge.
Positive edge.
Yes. So which means the values which are moving from lower to the higher. Okay. So these dotted lines are indicating that. So Q0, Q1, Q2, Q3, Q4. Okay. 0, 1, 2, 3, 4. Okay. These are our outputs. So my data. Okay. Now this second one is important. Okay. Data clock, of course, it goes low and high. Now my data input 1, 1, 0, 1, 0. Okay. This is going to be my input that I'm going to give here. So as soon as I give 1, okay, after the clock signal, this is going to come high. Okay, and here also it is 1, it's checking for clock signal, it is still high. This is maintained till the next positive cycle. Okay, so in the positive cycle, it's going to check the value is low. So from high, it is going to come to low, right? And it will next check at the next positive cycle, the value is 1 is going to come here. Next here, it's going to check the value is 0, so it is going down, right? So ultimately, what value I'm getting 0. Okay. So after how many cycles is this? 1, 2, 3, 4, 5. Now remember, this is very important of counting the number of clock cycles. If in case you go with another clock cycle, what is going to happen? Your data might vary. Say for example, if you take the data from here after this positive cycle, okay, what is going to happen? Your output instead of 0, what output will I get? What output will I get? If suppose I take the count here, what output is this? Is it 1 or 0? 1, right? So you should be very sure to count how many clock signals. So all that will happen based on the number of bits. Okay, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. After fifth only, you should find out what is your output. Similarly, for Q1, okay, for Q1, ultimately it's going to be a shifted version of this. Okay, whatever Q0 you got, it is going to be a shifted version. Okay, so the initial state is going to come here. Okay, so which means 1 is going to appear, and here the initial state is going to come, which means 0, and here the initial state is going to come, which is 1, and here the initial state. Okay, so this is continuing for 2 clock cycles, right? So in this clock cycle also it's going to shift, and I'm going to get the same 1. So this is my final output: 0, 1, 0, 1, 1. Okay, so it's in the opposite fashion. Okay, so my Q4, okay, my Q4 will be here, which is the most significant bit. Then Q3, Q2, Q1, Q0. So it's going to come in the same fashion. Okay, because Q4 is treated as most significant bit and Q0 is treated as least significant bit. So I hope all of you have understood this problem, right? So if I tell you to take a 5-bit data and represent with the help of waveform, you should be able to show all of this. Okay? You should be able to show the clock, and I might tell sometimes to use negative edge of the clock. Okay, so in that case, instead of seeing this rising edge, you will have to see the falling edge. Okay, at falling edge, you'll have to calculate and find out what is the value of Q0, Q1, Q2, Q3, Q4, and the final value should be represented. Is that clear, students? Can I move on? Is this problem clear?
Yes, sir.
Yes, sir.
Fine, fine. Thank you, students. So now we'll go to the next one, which is serial in, parallel out. This is also unidirectional, one way shift register. Okay. So I have my D flip-flop here. Okay, D flip-flop, same thing. D flip-flop, 4 D flip-flops, clocks are connected to each flip-flop. The only thing here is, instead of taking the data here, I am taking the data intermediately. That's the only difference. Okay. So here I'm getting QA, QB, QC, QD. So parallelly I'm getting my output. So as soon as the data comes in, okay, I'll be getting QA, QB, QC, QD. Of course, it's going to take some time in getting these outputs. Why do you think so? Because it needs to pass from one point to another point based on the clock signals, right? And then you will be getting this A, B, C, D outputs. So this is your serial in. You're giving data serially, okay, one after the other, but you'll get 4 bits together, okay, which is A, B, C, and D. So this is called serial in, parallel out, unidirectional shift register. Unidirectional because it's moving from left hand side to the right hand side. It's not moving from right hand side to left hand side. Okay, fine. So the same explanation is actually given here. The outputs are provided from each flip-flop, which means one the output of one flip-flop is actually the input to the other, right? Once information is shifted into the register, that is serial in, the information is available as a single entity, that is parallel out at the flip-flop output terminals. Since information is transferred into the register serially and after an appropriate number of shifts made available in parallel. So as I told you, it is not available immediately. Okay, it will happen only after the clock signals. So uh, after one clock signal, it is going to pass here, then the next clock signal and the next clock signal. So instantaneously, what I'm trying to say is instantaneously, you will not get your outputs here, right? You will get this at, few clock cycles, but then you're going to get them, in parallel. That is the idea. This type of register provides a serial to parallel conversion of information, right? So another application that we can think of is serial to parallel conversion. Whatever serial data I'm giving here, the same thing, I can get it in parallel. So serial to parallel converter. Okay. So this is one of the examples, okay, that we can look for in serial in and parallel out shift register. So I might ask you in the question, show the state of 4-bit register for data of input and clock waveforms. The register initially contains all ones. So how we will take this is, you can take any 4-bit data of 1, 2, 3, 4 4-bit data, because he is telling us to find out the state of 4-bit register, okay, for the data input and clock waveforms. The register initially contains all ones, right? So initially it contained 1, okay, so which means Q naught was 1 high, okay, then it's looking for my positive edge of the clock. The data is 0, it goes down, and then next cycle it's high, okay, so the same 1 is transferred, 1 is transferred here, 0 is transferred. Then at the next clock cycle, okay, what is going to happen is, whatever happened here, okay, so which means this part is going to go off, and with this clock cycle, whatever was there, okay, is going to get repeated. So it passes to Q1, okay, so, and then the low value, okay, and the high value continues as it is. Then for your Q2, okay, for your Q2 also, it is the same, okay, one is going to get continued. So what you can actually do is, you can put this in your diagram here, okay, you can put this in your diagram here, and you can try to find out what is going to be the values. First put 0, then there will be a clock, then the value comes here, then there is going to be a clock, then the value comes and sits here. So if you do that in that fashion, it becomes easy for you to find out the values here. Okay. So bit by bit you will have to analyze, then only it's going to be easy for you. Okay, can I move on? Students, can I move on?
Yes, sir.
Okay. So next, that we will be looking into is your parallel in, serial out, or parallel out unidirectional shift register. Okay. So this is your PISO, parallel in, serial out. Okay, serial out, and even we have the option of parallel out option, parallel in, parallel out, and also it acts like parallel in, serial out. So two functionalities are here in this unique shift register. Initially it looks to be complex, but then it's very simple. Okay, now as usual we are going to have 1 2 3 4 D flip-flops, okay, and we are just using a control here. Okay, we are using a control here, which is load or shift. Now let's talk about this in a while, and think of the clock signals first. Okay, so first we'll be giving clock, second clock, third, and to the fourth flip-flop. So clock is given, the the parameters are labeled, okay, A, B, C, D. These are done, okay. So next, now we can even uh, um, you know have two AND gates and a OR gate, okay. AND gates, OR gate, AND gates, OR gate, AND gates, OR gate. The reason is, I will tell you now. During the load and shift phase, which means, let us say, mm, I give a high value. So whenever it is a high value, the value will be shifted. So let's say 1 is given. Let's say 1 is given. So 0 will come here. If 0 is here, okay, whatever value that IA is taken up, it is 0. Okay, it is 0. And the output here is going to be 0. Okay, so input, whatever I give here, okay, so that is going to be multiplied with the value here, and it is going to come out. So which means, what is happening, it is not taking this load value. Load means what? Putting this values like this is my parallel load. Are you understanding, students? Okay, load is nothing but with these values: IA, IB, IC, input D. Okay, so this is used for load. Suppose I give a 0 value here. Okay, let us assume the other case now. So I give a 0 here. So if I give a 0 here, what is going to happen? 0 is going to come here. Whatever serial data I give, okay, that also becomes 0. Okay, ultimately it becomes 0 because 0 is here. Okay, 0 is here. So which means I'm getting a 1 here. If I get a 1 here, okay, it is accepting whatever values are here. So IA, which means input can be 1 or input can be 0. Okay, so that is been multiplied and then it passes. So that is why it's called load. Okay, when I say shift, then these are taken, these values are taken. So up till here, any doubts, students? Till here, any doubt?
No, sir.
Okay. So this is the reason, why we are using AND gate and OR gate. Okay. So if it comes from here, it is called serial data. If it comes from here, it is called a parallel data. Okay. This is serial in, this is parallel in. So the same thing happens here also. Okay. Because this line is connected, right? These lines are all connected. It is all a copy paste. Okay. This structure here, full thing is a copy paste. Okay. So you can take this whole structure here. Yeah. So this whole structure is a copy paste. Same values are here, same parameters are here, same gates are here, same flip-flops are here. So this is the first set. So first set, okay. This is my second set. It's my third set. And this is my fourth set. Okay. So same AND gates, flip-flops, and the connections. Okay. Right. So this is how I can either load the values or I can shift the values from one point to another. Okay. Now let us take the next case. Okay, so the value comes here to D and then it passes to Q. Okay, it passes to Q and here it is again connected. So here, as you can see, these lines are common, right? See, these lines are common. These lines are common. So ultimately, this is like accepting your serial data, whatever data has come here as the output. So that is again getting inside to your AND gate. Okay. So here you know that this is going to be my parallel out, right? We saw previously. But are we going to obtain A, B, C, D at the same time? Instantaneously, is it going to appear, students?
No.
No, it is going to happen after 4 clock cycles, right? So the first clock cycle, I'm going to get the output here in the next here, 2, 3, 4. So after 4 clock cycles, I'm going to get this outputs. So serial in is here, parallel out is here, okay, parallel in is here, okay, parallel in is here in the form of input A, B, C, D. So which means all this data passes and then I can either get a serial data out or a parallel data out. So this circuit is actually, a very clever circuit wherein it can accept parallel data. It gives me serial output. I can take even parallel output, right? So, this is how this circuit works. So any doubts here, students? Can I move on? Can I move on with this? Yes? Okay, thank you. So I have parallel data in, parallel data out, serial data in, serial data out. This small inverter acts like a switch. I can either load the values or I can shift the values. So it is like an on-off switch. Okay, right. So the explanation is given here, okay, for your reference so that it becomes beneficial for all of you uh, to understand the operation of the circuit that was just discussed. The operation of the register is controlled by load and shift line. Okay, so whenever it is low, zero value, then load operation is happening. Whenever it is high, then shift operation is happening. When a zero signal appears on this line, okay, which line? The load and shift line. The signals on the parallel data in A, B, C, D are transferred into the register upon occurrence of, this is important, positive edge of the clock. When one appears, then the flip-flops become cascade connection and it acts like a shift register, providing serial output. In this way, the register provides parallel to serial conversion. Okay, so how is this parallel to serial conversion? It can take parallel inputs here, okay, and it can give me serial output here. In the previous one that we saw, okay, it can actually do the reverse. It can take serial data inside and give us parallel data outside, right? So this is just the reverse, parallel in, serial out, or even parallel in, parallel out. So multifunctional circuit. By taking the outputs from individual flip-flops, it functions as parallel in, parallel out, unidirectional shift register. The register can also function as serial in, parallel out, unidirectional shift register, and as a serial in, serial out, unidirectional shift register. So as I mentioned, this circuit is very special. Okay, it can act as multiple things. Serial in, serial out, parallel in, parallel out, many things. Okay. So the next one is your universal shift register. So this is called universal shift register because it can shift right, it can shift left, or it can parallel load the values. So we call it as your universal shift register. So the circuit seems to be complex, okay, but then as we keep digging in, okay, it becomes very simple to understand. So we will have 4D flip-flops, 1, 2, 3, 4, 4D flip-flops, and we will be making the best property of a mux. Okay, so what is the best property of a mux? I can select as to which line is going to my output, right? I have multiple inputs here, and based on my select line, okay, based on my S1 and S0, I'm going to um, actually select which input has to appear at the output side and the output side, right? So here we'll be giving clock signal, okay, to each of the flip-flops. Clock signal is given. D is there, Q, Q bar, D, Q, Q bar, the same thing. Similarly, parallel outputs are also there, A, B, C, D. And then one additional thing that we have here is clear. Okay, so which means whatever data was there in the flip-flop, that will be reset to 0. Okay, so all the data will be flushed out. Right, so here we have inputs A, B, C, D. Okay, so these are your parallel inputs. And the select lines are actually connected to each other. So this is a 4:1 mux. Why is it called a 4:1 mux? Students, can someone tell me why is it a 4:1 mux? You have studied this, right? We have seen this in previous lectures. It takes 4 inputs and allows to pass only one single output. Right. Thank you. Thank you, sir. So that's the reason, it's called a 4:1 mux. So I have 0, 1, 2, 3, 0, 1, 2, 3. Okay, all these muxes are common. Okay, 4 input lines, 2 select lines, and 1 output line. So this output line is nothing but your F. Okay, the F that you see here, the function. Right. So I think now you have understood the structure of mux. You have understood the structure of D flip-flop, how the clocks are connected, how the clear is connected, how the parallel outputs are connected, how the parallel inputs are connected. Now, connections intermediate with the mux is important. Now the output here is connected to each flip-flop. Now that is common. Okay, output of the mux is connected to the input of flip-flop. And these inputs are only given at I3. Okay, it's given at I3. And your I1, okay, your I0 is connected to I1. Okay, your I0 is connected to I1. Similarly, here I0 is connected to I1. I2 in turn will be connected, okay, to I0. Okay. Similarly, here I2 will be connected to I0. I2 will be connected to I0. And I3 we know, okay, then here I1 is actually serial input for shift register. So if I give a 1 here, okay, if I give a 1, then actually it should actually work as your shift register. So as I told you, if it is 0, 0, okay, if it is 0, 0, then it will hold the value. If it is 0, 1, then it will shift right. If it is 1, 0, then it will shift left. If it is 1, 1, then it is going to parallel load. Now, what are these? We should only understand this, okay. Now, ultimately, okay, this is our universal shift register IC. Okay, so we will look about it and we will try and explain as to how this functions, okay, one by one based on this truth table. Okay, so we will have to look into this truth table here. Okay, wherein if it's 0, 0, then the value should be held. If it is 0, 1, then it should shift right. If it is 1, 0, then it should shift left, and if it's 1, 1, it should parallel load. Okay, fine. So now let us look at 0, 0. 0, 0 means I0 should be selected. So if I0 is selected, then what is to be done? The value is to be held. Okay. So let us say 0, 0, which means I0. Okay. So the value at I0 is actually, giving to I1. Okay. And here I0 is again connected to your, yeah. So what is to be done is 0, 0, right? So 0, 0 means I naught. So whatever is at my I naught, that will go at my F. So this will again pass through my D, okay, and it will pass through Q. So Q is now again connected to I1. So the same value is held. So whatever was the value of I naught, okay, let me annotate so that it becomes easy for you, right? So whatever was I naught, that comes here, okay, and the same value comes here. This value is connected to I1, right? Now what is to be done? I need the same value to be taken, right? So what I will do here is uh, it is to I1. Next 0, 0. Now here also if it is 0, 0, which means I naught value. So I naught value means what? I2 value, right? So I2 value means where is it connected? So let us say now I naught. I naught is taken the value of I2. Okay. So what is I2 here actually? It is I1. Okay. So this value comes here as my output. Okay. And whatever is the value here, okay, just a moment. Yeah. So whatever value is here, it is actually connected to I naught. Okay, can you see that? The same value, okay, the same value that you can see, okay, is connected and it is coming back in the form of a loop. It is coming back in the form of loop and this I naught is selected. So which means whatever value that I have here, okay, is being connected and whatever value I have here, the same value is taken and given to I naught and this I naught value comes here. So once this I naught value comes here, so which means this is happening as a loop. Okay. So the output is connected to I naught. See the output here, output is connected to my I naught. So I naught value will again go here. So if I naught value goes here, it is again like a loop. So 0, 0 means what? It should hold the value. So whatever is the value there in D flip-flop, okay, in a particular flip-flop, that is held. Okay, that is the meaning. Any doubts here, students, with this concept? Any doubts here?
No, sir.
Okay. So here the output ultimately is connected to I naught. So I naught means what? It is holding the value. Fine. Now let us go with 0, 1. 0, 1 means what? Shift right. So now we should look at 1, I1 here because it is 0, 1, right? 0, 1 means shift right. So 1. So serial input for shift register. So 1 comes here, okay, and the output is here, okay, and then the select line. So output 1 comes here, the select line, and then it comes as output, and then I1 is it is connected to I1, so I1 again comes here, okay, the output, and then I1 is selected, right? So which means it comes here, and then it goes to the output D flip-flop here, and then I1 is selected here because of the select line. Select line is 0, 1, so which means I1. I1 means it is taking the previous, right? So it comes here and finally at the output. So which means what is happening here? It is shifting from one point to another point. Shifting from one point to another point. So shift right is happening. Okay. Now let us take the other case. Okay, in the other case, which is 1, 0. 1, 0 means I2. 1, 0 means I2. Okay. So if I select I2, then what should happen? Okay, which means it should shift left. Okay, so I give 1 here. Okay, I give 1 here. So this comes. Okay, I2 is selected. So once I2 is selected, okay, just see your I2 here is connected to my output. Okay, so this output is actually this output is actually connected here. Okay, so which means it is shifting from this flip-flop to this flip-flop. Okay. So once it connects here, what is going to happen? I2 is selected, it comes here, gets into the flip-flop, and then it comes here, then this line is selected, and then it comes to I2, mux function D, then your QB comes down, okay, the same value comes here, I2, then the function output gets into the flip-flop here, and then finally I can actually get my output here. So which means my output which was present here got shifted from one point to another point. And what kind of shift is happening here? What kind of shift is happening? A shift left is happening. So which means, is it unidirectional or bidirectional? Students, is it unidirectional or bidirectional?
Bidirectional.
Bidirectional, right? Okay, thank you. Any doubts here, students? If you have doubts, then I can again get back. I can again explain. Let us take the last case now, which is 1, 1. Okay, 1, 1 means it should select the I3 values, right? So I3 values are all direct, right? I'm giving my input A, input B, input C, and input D. So which means it's a parallel load operation. So input A comes here, okay, then it goes to my flip-flop, mux output, then to my flip-flop. So it is loading. Similarly, here also it will come and it will load. Here also it will come and it will load the line. Okay. So what is happening here? It is a parallel load operation is happening. So based on my multiplexer, I can actually select what operation to be done, either to shift right or to shift left, okay, or to take these parallel values, or to just hold on to the same value. Ultimately, connections are important here, okay, how input lines are connected uh, with each other. Okay, so what you can do is you can actually take it step by step. You first draw the D flip-flops, okay, then after drawing the D flip-flops, then you take QA, QB, QC, and QD. Once this is drawn, then you can take the reset line, then you can take the clock line, and then you can take a 4 mux, 2 select lines, 4 input lines for all the 4 muxes, and the output of first mux to be connected to input of your D flip-flop, okay, and similarly the second, third, and the fourth. Now you have to work out with these input lines, okay. Always keep in mind your I1 will be shift right, and your I2 will be shift left, okay, and your I3 values will all be parallel inputs, okay. So this is clear. So the only connection that you will have to look into is your hold connection, okay, hold connection. So which means you have to create a loop here, okay. The path should be a loop here for I0. Create a loop. Similarly here for I0, if I0 is selected, then there you should see that a loop is created. A loop is created. So once that is done, then you can look of 0, 1, which is shift right. Okay. 0, 1 is your 1, okay, which is shift right. So if 1 is selected, the output actually comes here, and that should be connected to your I1. That should be connected to I1. So ultimately, if you do it step by step, you'll be able to analyze this circuit, okay, and you will be able to draw the connections appropriately. So students, any doubts with this universal shift register? It's a very important topic, okay. It can appear many times in your, it has appeared many times in your examinations. So any doubts here? Right. A bidirectional shift register, it is capable of shifting the contents either to the left or right, depending on the signals which is in the control input lines. Okay. The register is cleared asynchronously if a logic 0 is applied to label clear. So if I apply 0 here, okay, then it means it's all cleared. Okay, it's all cleared. Universal shift register, how does it function? Depending on the signal values on the select lines, okay, based on S1 and S0, it can actually take the values of inputs. The register can retain its current state, shift right, shift left, or loaded in parallel. Each operation of the result is on the positive edge of the clock. So this is about your shift register. And based on this, you can even have a few examples that can be asked, just like how we saw few waveforms, right? These waveforms. So similarly, you know, problems can be asked in such format. So we will see one example, okay, as to how we will look into the concepts. So the question is, incorporate a synchronous clear facility in a 4-bit serial in and serial out. So try to extract data from your question. So they are telling you that it's a 4-bit, which means you will have to employ 4 D flip-flops. Okay, 1, 2, 3, 4. Okay. 4-bit uh, serial in, serial out. So which means you know that it is shifting one after the other. Okay. Uh, Unidirectional shift register. So which means there is no possibility of the value getting shifted towards the left hand side. Okay. So configured using positive edge triggered D flip-flops. So question has a lot of data. Okay, so data only needs to be extracted. So what we will do here is incorporate a synchronous clear facility. So how can I, incorporate a clear? If all the data are present in the D flip-flop, how can I create this clearing concept of data in the flip-flop? So that's the question. So what we will do is, as usual, we will have this D flip-flops, okay, A, B, C, D. We'll connect the clock to them, okay. Clocks are connected to them, and then we will have this inputs, okay, DA, DB, DC, DD. Now the reason why we are having this AND gate, as we have seen previously, if I give a 0, then whatever value that your input is given is nullified, right? So if I give a 0, it is clear. If I give 1, then it is a shift, okay. So let's say, for example, that I give a 0 here. So if a 0 is given, okay, then what is going to happen? Whatever input is there, it is not going to take, and ultimately this is also connected to your clock. So which means it's all disabled. A, B, C, D, all these are disabled. Okay. But if I give a 1, okay, if in case I give a 1, then what is going to happen? Then what is going to happen? Clock is enabled here. Here also it's enabled, enabled, enabled. So which means this is functioning, this is working, this is working, and this is working. So once these clocks are enabled, okay, 1 is here. So now it is waiting for data here, because either if it is 0, then I'll get a 0. If in case it is a 1, then I will get a 1 here. So which means my data is actually getting transferred. It is not affecting just because I have a 1 here, right? So once I have the data here, with the next clock cycle, it moves here. Okay, and with the next clock cycle, it moves, and then to the final stage, it moves here. As we all know, your D flip-flop, whatever is the inputs, the same thing occurs at the output side, right? So cleverly, what we can also do is we can connect an AND gate here, okay, and check for the possibilities here. Either is it clear or shift. Okay, so if it is clear, then of course 0 is going to come here. If it is shift, then there will be a 1. So if it is a 1, then whatever value comes here, okay, QA, okay, Q value, so that is going to get multiplied and sent it to DB. Similarly, it keeps passing on from one flip-flop to the other, right? Okay, so students, any doubts till this concept? We will stop here, okay? And any doubts you can ask me. Is this concept clear? The example that we studied so far, is it clear? Yes, can I have a response? Okay, fine. So, this is how we go about understanding the properties of registers, okay, understanding the importance of your AND gate, okay. So we'll stop here and we will continue with the other examples that I have lined up in our upcoming classes, okay. So here also we will design a register which actually holds values, synchronous clear, complements the values, and does a circular shift right. So can someone tell me, for this operation, which type of register should I use for this operation? Just a simple question. What kind of register should I use? Should I use serial in, serial out, or should I use a parallel in, parallel out, or should I use a parallel in, serial out, or should I use a serial in, serial out, or should I use a universal shift register? Which is most applicable for this problem?
So serial and serial.
How do you say so?
The circular shift.
Sorry? Rohit, me loud. Rohit?
Because the circular shift.
Sorry, because it's not clear. It was not clear.
Circular shift.
Could you put it in the chat box, please? It was not clear at all. Circular shift. No, not a circular shift. I am asking which kind of register are we going to use? Are we going to use a PISO, SISO, PIPO, SIPO, or a universal shift register? Which is most applicable for this problem? Someone else? Anybody wants to answer that? Anybody?
Universal, sir.
Yes, good. Who was that?
Punet, sir.
Yeah, Puneet. So good, good. So we are going to use a universal shift register because it has functions here, right? 0, 0, 0, 1, 1, 0, 1, 1. So we need to use a mux. So if we have to use a mux, okay, then it is going to be a universal shift register. So we will discuss this extensively in our upcoming classes, and we will try and understand, okay, as to how we can employ such functionalities.